This example is from MGF 1107, section 14.2, where we discuss finding Euler paths and Euler circuits. In this example, we're given the following graph that has 5 vertices, A, B, C, D, E, and we are asked to construct an Euler path that starts with vertex D. Now, before we do that, let's look at the degree of each vertex and see if we can use Euler's theorem, which discusses the degrees of the vertices and whether we have an Euler's path or an Euler circuit. So in this problem, A has a degree of 1, 2, 3, 4, so that's even. B has degree 1, 2, so that's even. C has degree 1, 2, 3, and 4, so that's even degree. D has degree 1, 2, 3, so that's odd. And E has degree 1, 2, and 3. So according to Euler's theorem, if you have two vertices, exactly two vertices, that are odd, your graph has at least one Euler path, probably many others, yet it will have no Euler circuits. To have an Euler circuit, you need to have all your vertices have an even degree. Now, what Euler's theorem mentioned is if you do have two vertices that have odd degree, your Euler path has to start at one of those odd vertices and end at the other one. So in this problem, we know that our Euler path, at least one Euler path, will start at D. And the path, the Euler path, which must traverse or use all the edges in the graph, will end at E, because that's the other odd vertex. So there are many Euler paths that probably exist. We have to come up with one Euler path. So we know the answer is not C, because we do have an Euler path. It's going to start at D and end at E. We just have to find one of them. Well, this problem's pretty close to being done, because it can't be B and it can't be D either, because those start at D and end at D. But according to Euler's theorem, if you have two vertices that are of odd degree, your path is going to start at one of the odd vertices and end at the other. So we should have a beginning at D and ending at E. So let's just verify that option A is the right option. Let me get a little thicker pen here. Pick on yellow maybe. So let's follow this path here. So let's go D to E, all the way to A, back to D, right here, back to D, then to C, then to A, to B, to C, and E. And let's see if every edge is colored or traversed. And it looks like the path that we used in A is an Euler path. We have used every single edge of the graph exactly one time, and our path begins at D as desired, and it ended at E as we thought it would according to Euler's theorem.